The divergence theorem is the fundamental theorem of calculus applied to divergences. What it tells us is that there is an equivalence between the divergence of a well-defined vector field over some volume. So we take the integral of the divergence of v d tau, and that will be equal to that vector function on its surface. And we have seen in other videos that we can break our volume up into little tiny cubes, and each of these little tiny cubes has some divergence associated with them. So they're all coming out. And when we put these cubes together, all of the inside cubes, so the divergence here and the divergence here, will exactly cancel out. So, kapow! They go away, and this pair goes away. And kapow! This one goes away, and kapow! This pair goes away. And all of this winds up just being equal to whatever we had on the surface. Now what this video is going to do is it's going to show a specific example where we're going to integrate a particular vector field on the surface, and we're going to take the divergence of that vector field and do our volume integral. What we're going to start with is the area integral over some closed area of our vector field v dotted with dA. And the specific v that we're going to use, v is going to equal z x hat plus y squared x y hat plus x z z hat. So we're going to find this v dot dA over some entire cube, and that cube will be, as it shows there, the cube in the first octant of edge 2. So it's going to go from 0 to 2 in the x, the y, and the z direction. We're going to break this volume integral into the 6 faces of the cube. So that's going to wind up being the integral of v dot dA on surface 1 plus v dot dA on surface 2 plus v dot dA on surface 3 plus v dot dA on surface 4 plus v dot dA on surface 5 plus v dot dA on surface 6. Note, this was an enclosed surface. That's what the circle here means. And these are the 6 individual faces of our cube. Now for surface 1, dA, for surface 1, dA is going to be equal to dy dz x hat, and surface 2, dA will equal minus dy dz x hat, and for surface 3, dA will equal dx dz y hat, and for surface 4, it will equal minus dx dz y hat. And for surface 5, dA is going to equal dx dy z hat. And of course for surface 6, we have the only one that's left, minus dx dy z hat. Notice for surface 2, 4, and 6, we've got this minus sign. And this minus sign can be thought of as going in the x hat direction. So while this one is pointing in the positive x direction, this one is pointing in the negative x direction. The positive y hat direction, the negative y hat direction, the positive z hat direction, the negative z hat direction. Also note dy dz. This is a little tiny square, so that's our dA, and this is the vector part. So this is our area increment, and this is what gives us the direction. We've taken a moment to reorganize where things are. So we have our closed integral, our 6 broken out faces of our cube, our differentials, and of course, the vector function that we're actually using. So when we do this, let's take a look at this one specifically. This is going to turn into the integral where x equals 2. So y is going to go from 0 to 2, and z is going to go from 0 to 2, but x equals 2 everywhere here. And then we have v dotted with this particular integral, differential, which is dy dz x hat. Because we're taking the dot product, and this is just pointing in the x direction, this dot product becomes the x component. So we're going to integrate the x component of v, dy dz, on the surface where x equals 2. We are going to do this for each of these 6 different integrals. So all of this will wind up being equal to vx dy dz, where x equals 2, minus, note the minus sign right here, and surface 2 is where x equals 0. But once again, it's vx dy dz. Then we're going to add that to this surface right here, and this surface is where y equals 2. And we're going to have the dot product, but this time, because we've got the y hat, we're going to get a y component of v as opposed to the x component, and that's going to leave us with dx dz. Subtract off for surface 4. This is where y equals 0. Once again, we have vy dx dz. And unsurprisingly, now with surface 5, this is where z equals 2. And once again, from our dot product, we're now going to have the z component, dy dx minus, because there's a minus sign, where z equals 0, vz dy dx. Well, our vx is actually something very specific. In this case, because the x component of our v is just z, what we can do is we can plug in z for the x component of v. And we can plug in z for the x component of v, and our y component of v is going to be y squared x. Then the z component of v is going to be xz. So we can substitute in here and here. xz, xz. Now we have 6 different integrals, but there is no explicit x dependence here. There is no explicit x dependence here. So the fact that x equals 2 and x equals 0 for this particular integrals doesn't matter. And of course, what we can say is that because this integral and this integral are now identical, they cancel. Well, that's kind of neat. In this case, y equals 2. So every place we see a y, we can substitute a 2 in, and 2 squared is, of course, 4. But here, y doesn't equal 2, y equals 0. And because y equals 0, this entire integral just goes to 0. Here, z equals 2, so we can erase this z and replace it with a 2. But here, z equals 0. So because z equals 0, once again, this entire integral goes to 0. We started with 6 integrals. These two canceled. These two went to 0. We're now left with just these two integrals. Once again, we took a moment to reorganize where things are. These two integrals canceled. This integral and this integral were both 0. This is the integral we're left with. And our limits of integration are going to be from x equals 0 and z equals 0 up to x equals 2 and z equals 2. Here, it's going to be from x equals 0 to y and y equals 0 to x equals 2 and y equals 2. That comes from the fact that we're integrating over a cube that's sitting in the first octant between 0 and 2. Doing this integral right here is fairly straightforward. We get x squared over 2 times 4 gives us 2x squared. And then, of course, the integral with respect to z gives us z, evaluated from 0, 0 to 2, 2, plus integral of 2x is, of course, x squared. And the integral with respect to y is going to give us a y. And once again, we're going to go from 0, 0, up to 2, 2. Plugging all of this in, we have 2 times 2 times 2 times 2. And of course, that's 2 to the 4th, or 16, minus 0, plus 2 times 2 times 2, which is 8, minus 0. So 16 plus 8 gives 24. Now we've worked out one side of the equation, we have to work out the other side of the equation. Now we need the integral of the divergence of our vector field v evaluated over d tau. Well, this is going to be equal to the divergence of v. So the divergence of v is the x derivative of z, which is 0, plus the derivative of the y component with respect to y, which is going to be 2yx, plus the derivative of xz, the z component of v, with respect to z, so x. Now this is a volume integral, so we have a triple integral, dx, oops, don't need that comma, dx, dy, dz. Our limits of integration are still given by the same box. So we're going to go from x equals 0, y equals 0, z equals 0, up to x equals 2, y equals 2, z equals 2, giving us one nice triple integral to do. And of course, this integral winds up becoming x squared, y squared, z, divided by 2. And then this component becomes x squared, y, z, also over 2. And this whole expression is going to be evaluated, as I said, from 0, 0, 0, up to 2, 2, 2. So that means we have 2 squared times 2 squared times 2 divided by 2, which is 16, plus 2 squared times 2 divided by 2, which is 8, minus 0 times 0 times 0 over 2, plus 0 times 0 times 0 over 2, so minus 0. And this, of course, is now equal to 24. Well, that should fill us with a certain sense of déjà vu, because when we did the area integral over all 6 of our different square faces of our cube, we wound up getting 24 as well. So what we showed was that this is equal to this. This video showed an example of the divergence theorem, that this will in general be equal to this. This further went on to say the integral of a vector field over a particular closed surface is going to wind up being equal
to the integral of that same vector field's divergence over the volume that is enclosed by that surface. A later video will explore how we can derive this relationship.